Hello everyone, today we'll be talking about case study 4, which is the control systems design project. So for this design project, we were challenged with reducing the peak time to 75% of the original while maintaining the overshoot and response time. So most of the baseline variables can be found with the equations on the top right, which is zeta, TS, TP, and then the overshoot percentage. Using these variables, we can find the pole locations, which is at -3 or -1.33 plus 2.2 j. That is found from the equation negative zeta omega n plus omega n times 1 minus zeta squared. All that the square root of all of that. We can also find the gain needed, which is K, and that number is 11.3257. The overall compensated K is found using the equation S plus Z over S plus P times S squared plus times G of S. G of S is the function, the overall function. Z and P are the pole and zero locations respectively. So in this system, we can either design an active or a passive system. An active system requires power, but it also shuts off when not in use. A passive system does not require power, but it is always on. For this project, it is a lane switching device. For this, we would want an active system rather than a passive system, because you do not want every slight turn that you make interpreted as a lane change maneuver. This graph here shows the response time in terms of the compensated system in blue and the uncompensated system in red. The uncompensated system has a very heavy response, but then drops off quickly, and its steady state is 0. The response for the compensated system spikes up and is a bit slower to reach the peak time, but overall levels off with a response of 1. These are the actual results, and then the expected result would be an overdamped system, as was seen in the example image given. An overdamped system is what you would expect to see, but with this we ended up getting an underdamped system. This is mainly because the underdamped system does not take as long to reach the peak time, or does not take as long to reach steady state, sorry. And an overdamped system takes a bit longer to reach the steady state system. When you're dealing with a maneuver like this, you want something to be as fast as possible. So now I have explained to you the results of the system compared to the uncompensated system, as well as the design requirements for the major parts of the system. Thank you for listening.